Good morning, students. I'm Dr. Shiva. So, this is our second video. In the previous video, we have seen about single degree of freedom system. Okay, and we have seen the concept about lumping mass concept, and we have drawn the mathematical model for single degree of freedom system, and we have seen how to draw free body diagram and how to formulate the equation of motion for single degree of freedom system. And in this video, we are going to see what is 2 degrees of freedom system and how to draw the mathematical model for the 2 degrees of freedom system and how to formulate the equation of motion for 2 degree of freedom system. So as we know that a degree of freedom is the number of coordinates required to represent the new position of the body after subjected to some kind of force, right? So for single degree of freedom system, we have seen the example of a pendulum, okay? And if you take the portal frame example, we have seen a single bay portal frame which is subjected to a horizontal force. Because of this horizontal force, there is some possibility for swaying action which can be represented using one coordinate, okay, along x-axis that we have seen. Okay, the same concept if it is applied for G+1 building. Okay, say this is a G+1 building. Okay, so here the floor mass of this floor is m1 and mass of this floor is m2. So we know that the effect of wind will be there at higher heights. Say if you are going beyond 10 meters height, the possibility of wind effect we have to consider in the analysis of a structure. Okay, so the wind effect can be different for this floor as well as this floor. For example, say if a force is applied here, okay, a wind force is applied here. Because of this, there is some possibility for swaying of this entire structure. Okay, if I draw this sway structure, you can have a swaying action like this. Okay, in which you need to have one coordinate here at this point and another coordinate at this point. Okay, so one x coordinate I require to mark this position, say x1, and another coordinate x2 I require to mark this position. Okay, it's not like single degree of freedom system. If I want to specify this new position, obviously I can use one coordinate to represent the axis or the position of the structure. But in case of this G+1 building, I can't use one coordinate to represent the new position. I need at least two coordinates to represent the new position of the structure. Okay, so here since I need two coordinates to represent the new position of the structure, obviously it is called 2 degrees of freedom system, right? So here, if I draw the mathematical model for this particular structure, you can see there are two floors, right? One floor is here and another floor is here. As we have seen in lumped mass concept, we will be drawing a lumped mass like this. For this single degree of freedom system, I have drawn a lumped mass like this, right? And if I want to draw this for this 2 degrees of freedom system lumped mass m1, I have to give a lumped mass here, and m2 I have to give a lumped mass here. So this will be m2 and this will be m1. Since this column will be having some stiffness, stiffness will be different for this column and this column, because the load taken by this column will be different and load taken by the bottom column will be different. Okay, and because of that, stiffness will be different for this column as well as this column. So I'm going to represent the stiffness for this upper column as k2 and the lower column as k1. Okay, So for this particular structure, I'm going to draw the mathematical modeling. So I'm going to show a spring element, and I'm going to draw the first mass M1 with a roller. Okay, and second flow, I have another stiffness, right? So I have to specify the second mass like this, M2, and I have to specify this roller here. So the stiffness of this column will be K1, and stiffness of this column will be K2. So here you can see there are two stiffness, for two masses. Okay. So now to formulate the equation of motion, we have to draw the free body diagram. Okay. Since what we have done for single degree of freedom system, here also we are going to draw the free body diagram. Say I'm going to take the mass M1 here. For this M1, I'm going to draw the forces which are going to act on this. So we have seen in the single degree of freedom system, obviously because of the motion, okay, because of some motion displacement, okay. So I'll be having some displacement here and x2 displacement here, right? So obviously I'll be having inertia force, that is mx1 double dot. Okay, this I got from Newton's second law of motion, and stiffness spring force will be there, which will be acting opposite to the direction of applied force, and this K1 will be having Kx1, K1 x1, and this is M1 x1, K1 x1, right? And here I have stiffness. Okay, in the single degree of freedom system, I may not have this portion. I'll be having only this portion. Okay, so I will not draw any force here, but here there is an additional stiffness is here. Because of that, I'll be having a average, that is stiffness effect will be there, which is K2 of x2 minus x1. Okay, so that kind of stiffness force will be acting at this position, right? So if I take M2, we want to draw the free body diagram. So obviously there will be some inertia force for this mass M2, that is M2 x2 double dot will be there, and I'll be having this stiffness. Stiffness will be same as this one, that is K2 of x2 minus x1, and this position is free. There is no external force or something here. Because of that, I won't have anything here at the right side. Okay, so now to uh, formulate the equation of motion, I have to resolve this in the horizontal direction. For this, so I'll be getting m1 x1 double dot plus k1 x1 minus k2 of x2 minus x1 equal to 0. Okay, so here I'm going to simplify this. M1 x1 double dot k1 x1 minus k2 x2 plus k2 x1 equal to 0. I'm going to take x1 common. So m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to 0. Okay, this will be the equation of motion for the first mass. Take this as equation number 1. If I take the second mass, okay, if I resolve for this, I'll be getting m2 x2 double dot plus k2 of x2 minus x1 equal to 0. So just bring in k2, m2 x2 double dot plus k2 x2 minus k to x1 equal to 0. I can just rewrite this m2 x2 double dot minus k to x1 plus k to x2 equal to 0, and this will be equation number 2. Okay, so this is how you can formulate the equation of motion for 2 degrees of freedom system. A quick recap. So here, this is the structure for 2 degrees of freedom system, in which I'll be having two coordinates to represent the new position of the structure. Okay, that's why it is called 2 degrees of freedom system. And the mathematical model, so I have two masses m1 and m2, which I drawn here, m1 m2. So stiffness will be there. This column will be having a stiffness k1, and this column will be having a stiffness k2. So that's why it is drawn like this. And drawing the free body diagram, so m1, so I'll be having inertia force, then stiffness force will be there, and here stiffness of this column will be here. Okay, and if I take the m2, I have inertia force, inertia force, spring force, and there is no force at the right side. And I have to do the resolving of forces in the horizontal direction to get two equations of motion. Okay, since I have two coordinates, that is two unknowns, obviously I have two equations of motion for 2 degrees of freedom system. Okay, hope you have understood. So if you have any doubt, put it in the comment box. Okay, thank you so much.